to summarize what we have done so far, okay, we have done the following. Number one, we have discussed, right, what's a random process. Random process, okay? And we have said that a random process is a random variable which has variation with time, right? So based on that, a random process possesses two properties. It has statistical properties, right, which are described by probability density function, right? So the distribution, right? The mean, mu of x, the variance, right? Sigma of x, the autocorrelation function, Rx of tau, right? And so on. All of these are statistical properties of the random process. And it has time properties, right? Why it has time properties? Because it's a function of time, right? And some of these important time properties are, if my random process, let's say my random process is called x of t. Okay, so this is my random process. So if my random process is called x of t, I have the time average of that random process and the time average of x of t times x of t minus tau or plus tau. Okay? And typically we put the other one conjugate in case that random process is complex as well. Okay? So this is the time average of the random process itself, and I'm taking the average here over time. So I integrate over time and I divide by the total time duration, right? And the time average of the autocorrelation function. So this is the time average of the autocorrelation function. I take the value of x of t multiplied by x conjugate of t plus tau, and then I average that over time. So I integrate this over time, t, and then I divide by the total time duration. While when I'm doing statistical average, so mu x, right, and Rx of tau, I'm doing averaging over the probability density function, right? So this is defined as integral of x of t multiplied by f of x, the probability density function, right? Which is generally might be a function of time as well. And then I integrate with respect to x, right? So that I get statistical properties. So f of x, sorry, x of t is a random process, which means that in addition to being a function of time, x itself is a random variable, right? And because x is a random variable, if I want to get its mean value, what do I have to do? Multiply the random variable by its probability and integrate, right? Over what? Over the random variable itself. Okay? Similarly, if I want to do Rx of tau, this is the integral, typically double integral, but we just write it as one, because if we have more than one variable, we have more than integral. So it's an integral of, right, x of t times x of t plus tau or minus tau, doesn't matter, shift up or down, it's the same thing. And then you multiply by f of x, right? And typically these are joint distributions between x of t and x of t plus tau, okay? And you integrate with respect to x again. And if it's x of t and x of t plus tau, two random variables, then you integrate over dx of t plus tau, okay? So if you have different distributions for different time shifts, you have to use here the joint distribution, and you have to integrate here over the two different random variables, this one and this one. Okay? In most of our problems, these two are going to have the same distribution. So they are samples of the same random variable, and since this is the case, we only multiply by f of x and integrate with respect to one variable. And that's what we did in the example last time, right? So now we have what? We have on the left side statistical properties. On the right side, time properties of your random variable. By the way, does everyone know how to calculate this? X of t average and x of t times x conjugate of t plus tau average over time? Yeah, how do you calculate this?
Integrate from negative infinity to infinity.
So, what? Sorry? I didn't get.
Integration divided by t.
Okay, so exactly. So you integrate the function over time, and then you divide over the time duration. So if you want to write these, I'm going to write them. Okay. I'm trying to make this more organized. So let's see if I can. I don't want to delete. I can't do much. Okay. So anyways, I'm trying to select some. Okay. So let's try to shift these left. Yes. So x of t, let me go back to writing. So this is equal to limit. Typically it's written this way, right? T goes to infinity, right? And then you integrate from minus t over 2 up to t over 2 and x of t dt, right? So you are just saying here, you are doing this limit just to say that, oh, and all of this is divided by t. So 1 over t here, okay? So you are saying, I'm integrating over the whole, this means over the whole range of the function, right? So if x of t is from 0 to 20, you will integrate from 0 to 20. If it's from minus 90 to plus 25, you will integrate from minus 90 to plus 25 and so on, right? So you are integrating over the whole range of this function and then dividing over the range, right? This will give you the time average of the function, right? Same thing here, but instead of x of t, it's going to be x of t times x of t plus tau. And then again, 1 over t, and you integrate from minus t over 2 up to t over 2, okay? So this is clear to everyone, and I'm going to write it as well. So limit as t goes to infinity, 1 over t, and you integrate from minus t over 2 up to t over 2, and you have inside x of t, x conjugate of t plus tau, and you integrate with respect to dt. Okay. So that's how you calculate the time. This is how you calculate the statistical. Okay. Now, based on the statistical properties only, okay, also what we were doing last time, okay, we can classify our random processes. So if this is the class of random processes, right, so random process in general, assume that this is a big class of functions that are called random process, okay, which has statistical properties as well as being functions of time, okay. Inside those, there is a smaller class called wide sense stationary random process. How do you know which random process is within this inner class and which random process is outside this inner class? By testing the statistical properties of the random process. So, a random process, right, is wide sense stationary if and only if. Okay? Number 1, mu of x, so a random process x of t. Call it x of t, okay, is wide sense stationary if and only if mu of x, right, is constant, which means not a function of t, not a function of time, okay, and so both conditions have to apply, and, right, second condition, if Rx of x of t, and we call it, okay, let me write it in the same notation that we had last time. So we call this as Rx of t and t plus tau, right? Okay? Is equal to Rx of tau only. So it's a function of time shift. Tau only, and not a function of time t, right? So basically, if this is my time scale, and I pick a point at t, and another point at t plus tau, right? And I get the autocorrelation between those two, they will give you exactly the same autocorrelation if I calculate some t1 and t1 plus tau. Okay? So if I calculate the autocorrelation between t1 and t1 plus tau, I will get exactly the same value if I calculate it between another t and that t plus the same tau, right? So it only depends on the shift. Doesn't depend on the start point, whether I start at t1 or I start at t, right? It only depends on the difference between the start and the other point, right? And the start and the other point, okay? Got the idea? خلاص? So if a random process satisfies condition 1 and condition 2, then that random process belongs to the White-Sims stationary, okay? Now, what we have looked at last time as well is the ergodicity of the random process, right? The ergodicity means that, okay, so for a random process to be ergodic, there is another set of conditions. So it's White-Sims stationary if these conditions, and it is ergodic, right? If, right, mu x equals x of t average, right? So I do here, mu x is the statistical average. It's equal to the time average of the random process. And, right, Rx of tau is equal to the x of t plus tau averaged, right? I wrote this in a funny way. X of t plus tau. Okay? And the conjugation should go here, just to be more accurate. Okay? So if the statistical average is equal to the time average, and the second order statistical average, which is the autocorrelation, is equal to the second order time average, right? If those two conditions are true, this is an ergodic random process. So basically, if you go to that classification, you will find that ergodic random variables are even an inner set inside White-Sims stationary. So I can say that this is called ergodic. So I can say that any ergodic random process is by default a White-Sims stationary random process, right? And of course, any White-Sims stationary random process is a random process, right? Okay. But not every White-Sims stationary random process is ergodic, right? So keep this in mind, okay? Ergodic is a more strict classification, okay? So any random process that you can prove it is ergodic, by default, it's already White-Sims stationary. You don't need to do the other proof, right? But if you prove it is White-Sims stationary, you are not sure whether it's ergodic or not, right? That does not necessarily mandate that it is ergodic, okay? And the easiest thing is just remember these layers, right? So the biggest layer is random process. Inside them is the set of White-Sims stationary random processes, and then inside that is the ergodic random process, okay? Any questions so far? That summarizes what we have done last time. One remaining thing is the time and frequency relation for White-Sims stationary random process. So the last thing that we studied was that for White-Sims stationary random process, right, we can find, right, the power spectral density of the random process by call it Sx of f, right, by Fourier transform of the Rx of tau. Okay? So if I have Rx of tau, right, I can do Fourier transform for that one, right, to get Sx of f, and of course vice versa, right? I can do the other way around by the inverse Fourier transform, right? This is true only for White-Sims stationary random process. Why? Yes?
Yes, by Fourier transform. What?
Fourier transform of this.
Okay.
Okay. So why this is only defined for white-sense stationary random process? Because again, just simply, without going into mathematical details, for white-sense stationary random process, Rx is a function of tau only, so it's a function of one time variable, the shift, right? If it was not white-sense stationary, this would have been a function of t and tau, the start point as well as the shift. Now, which one you would use as your time variable to do the Fourier transform? If you use one and take the Fourier transform with respect to t, for example, you will still get here Sx of f and tau. So it's going to be a Fourier transform which is a function of time, right? This is quite confusing. I mean, you cannot really say that this is a power spectral density. Power spectral density at which time describes what kind of power spectral density, right? So this definition, as far as we are concerned, is only true or can only be done for white-sense stationary random process, right? And in that case, the autocorrelation function, right, is the time domain representation of the power distribution, and the Sx, or the Fourier transform of that, is the frequency domain representation of the power distribution, which we call it the power spectral density. So power per unit frequency, right? And this one is going to be power per unit time shift. Okay? Any questions so far? Okay. So let's try to go back to our examples. Okay. So now, why do we care about representing our random process, whether as power spectral density in frequency domain? Yes. Why do we care about representing our random process, whether by looking at its power spectral density, so power versus frequency, or by looking at its time autocorrelation function, which describes the variation of power with respect to time shift tau, right? Why do we care about this? Again, I mentioned this last time, but here we show this in more systematic way. Our communication system, whether you are talking about the channel or you are talking about part of the blocks of your communication system, they are all linear time invariant systems, right? Now going back to your signals and systems, the projector goes into, doesn't like signals and systems, right? Okay, so we are dealing with communication systems that are typically linear time invariant systems, right? The nice thing about linear time invariant system is that we can represent the output as a function of the input and the function of the system, right? Now for random processes, can I deal with the first order representation of the random process, particularly in frequency? I can. Why? Because if I look at the first order, like the x of t as it is, okay, then I'm going to look at what? I'm going to look at something which is random. I cannot deal with this, right? I don't know the value at any point in time, right? So how do I get rid of randomness? I try to take averages, okay? Now the problem is, for most of our communication systems, if you take the average, right, it's going to give you something which is not a function of time. So all your time representations of that random process, okay, you will not have it represented in your first order average, the my, or the mean of the input or output. So x is the input and y is the output from this linear time invariant system, right? Again, typically if my random process is stationary, this means that this mean is a constant. We said for stationary random process, the mean is a constant, right? If it is a constant, I just totally forgot about the existence of time variation, right? And my random process, the information about my random process is totally lost. I have nothing that represents the time variation of this random process, right? The good thing about the second order, which is the autocorrelation function, is that it still represents the time property of my random process in terms of what's the relation between the time process at this time, right? And the time, the random process at a shifted time. What does this represent in reality? يعني فكر كده, when I take the autocorrelation, okay? And for example, I find that my autocorrelation looks like this. Let's say I calculate this autocorrelation and I find that it looks, for example, like this. Right? What does this represent?
Most of the values are going to come around some.
Not the value. Don't forget that the autocorrelation is the relation of the expected value of the current and some shifted version of the random process, right? And our x-axis here is going to be what? Tau, the shift, right? While my y-axis is going to be the autocorrelation value, Rx, right? So it tells me that as I go further, right? So as I sample the random process at a particular time t, every sample of the random process is a random variable, right? As I sample as a particular time t, and then sample at a shifted time t plus tau, right? I get what? I get a smaller value as compared to sampling close to the original sampling point, right? So the highest value is going to be when I take the sample at time t and then again at time t, right? I'll have the highest value of autocorrelation. As I take a sample at t and then another sample at t plus tau, as I increase that tau, I will get something dropping, right? Which means that I will start having a random process which is quite uncorrelated, has no linear relation with the original sample process, right? And then if I go further, I will have another random process which has less correlation with the original one, and so on. So it tells me that after a while, I will get something totally unrelated to the original one, right? And that's, you remember when we talked about, in the last lecture, we talked about the properties of Rx of tau. We said the peak value is at 0, and then any other value is going to be less than that peak or equal. And if it reaches this value again, it must be periodic. You remember? It will reach it every same duration, right? So the important part that we care about is the fact that this is the highest, and any other one is either equal to or less than that point at tau equals 0, right? Okay. So this is in time perspective. I still maintain the time dimension by the second order statistics, right? But the good thing for white cell stationary is that this time dimension is not dependent on where do I start. I start at any point, then the shift is what controls my autocorrelation function, not where I started taking the sample, right? Okay. So I ended up with some expression which is proportional to the second order value of the function, because Rx of tau includes x of t times x of t plus tau. So it's as if it's proportional to x squared, right? So it's proportional to the square of the magnitude of the function, right? And it is still shows me the effect of time variation, but only in terms of the shift, right? And the good thing is that in this case it has only one time representation, the shift. So I can have it as a function of time, and I can have a Fourier transform for that as a function of frequency, right? And because it's proportional to the square, then it represents power rather than magnitude. Okay? Now having this, I have a time function which is proportional to square the magnitude. Its Fourier transform, which is Sx of f, right, is the frequency representation, and again it's proportional to square the magnitude, so it's power versus frequency. Okay? Now this is exactly the same as the power spectral density of deterministic signals, right? Because it has the same properties. It's proportional to the square, right? It's no longer random because I took averages, right? When I calculated this or this, I already took average over all probabilities, right? So I ended up with a deterministic value, right? So it's deterministic, proportional to the square of the signal, and in time domain it's a function of a time variable, in frequency domain it's a function of frequency variable. So I ended up with something that represents my random process in a very similar way that you do for a deterministic function, right? Okay. So now, if I have, assume that this is not a random process. Let's start by a deterministic function. If I have x of t going to the input of a linear time invariant system, and the output is y of t, okay? And both of these are deterministic. Okay? So in this case, I can represent y of t as a function of x of t by saying what? In time domain, y of t is equal to x of t convolved with h of t, where h of t is the impulse response of my linear time invariant system, right? If I go to frequency domain,
X of f
X of f multiplied by h of f, right? But this is if I can deal with the first order, right? The problem here is that R and S are the second order. You remember also from signals and systems, if you have, right, x squared, or the power spectral density, you call it in that case S of x. Right? If you have S of x as a function of f, right, at the input, and you have y, sy, right, of f for the deterministic function as the power spectral density of your output. What's the relation between those two? You remember that from your signals and systems or not? If I know the power spectral density of the input, where this input is deterministic, so the power spectral density is simply square the Fourier transform, right? And I know the power spectral density of the output, right? How do you relate those two together? What's the relation?
The square of the impulse response.
Square the magnitude of the impulse response, right? So the relation says that Sy of f is equal to Sx of f, right? Multiplied by h of f magnitude squared, right? That relation is the relation between the power spectral density of the output as a function of the power spectral density of the input, right? Okay. Similarly, now I ended up representing my random process, which is x of t, right? The input random process x of t, instead of being deterministic, it's random, right? But in the second order, if I represent it by r in time domain, becomes Sx in frequency domain, I still have a power spectral density of the input, right? Then I can immediately calculate the power spectral density of the output using exactly the same relation, right? So this relation is true whether x is random or x is deterministic, right? But only possible to use when x is White-Simms stationary. Because if it is White-Simms stationary, I can calculate a power spectral density for it, and I can calculate an autocorrelation function, which is a function of the shift only. Okay? So while we were doing all of this and figuring out the stationary random process and then looking at the autocorrelation and the power spectral density, because once I was able to represent my random process as second order variable of frequency, which is power spectral density, or second order variable of time, which is the autocorrelation, I can now apply it to the linear time invariant system and figure out the output power. I cannot figure out what's exactly the output random process itself, but I can figure out the output power, right? Okay? Any questions so far? To simplify this, okay? If I tell you, for example, if I tell you that I have a random process x of t, right, which has, for example, Rx of tau, which is equal to n naught times delta of tau, right? N naught over 2, for example, times delta of tau, okay? And I ask you, okay, what's gonna be, so this is x of t going into this system, right? And the output of this system, by the way, if you have a random input to a system, what do you expect at the output? Random, right? So the output is gonna be a random process, call it y, right? Y of t. And then I ask you what's, and this system is delta of t minus 3, okay? And then I ask you what's Ry of t, of tau. Okay. So how do you calculate that? I skipped the slide for the time case, okay? So how do you calculate that? Okay, yes, okay.
Then I use h squared times Rx.
So
First we need to find h of f.
okay, so h, this is h of t, is that right?
Yes.
This is our h of t, correct? So I will say, okay, and this is Rx of tau, right? And what's required is Ry of tau. The relation that I know in frequency says that Sy of f, right, is equal to Sx of f times h of f magnitude squared, right? So what do I need to find? I already have this, which is immediately the Fourier transform of Rx, right? This Sx of f is the Fourier transform of this, right? And if I want h of f, it's simply the Fourier transform of this, right? And then I can square the magnitude of that, multiplied by s, I will get Sy of f. Then do what? Inverse Fourier transform will give me Ry of tau. Do it. يلا. بسرعة بس عشان نلحق نخلص ونعمل الكلام اللي قلنا عليه كله. So you have 3 minutes, do this. Inverse Fourier of this. So you are given Rx of t, Rx of tau. What's wanted is Ry, the output autocorrelation function, right? And you know the impulse response of your system. And the relation is there. So from that relation, you can get the frequency from the frequency, and then you reverse it back to time. The function n naught over 2 multiplied by delta of tau. By the way, you can, sorry, so don't get confused. في الآخر tau or t here are going to be your time variable. So you can assume that this is delta of t and this is, or vice versa, delta of tau and this is delta of tau minus 3. Your time variable will be tau. خلاص. خليني حتى make this so you don't get confused. خلاص. You don't assume that these are two time variables. They are the same random variable. And everything here is going to be as if tau is your time variable. Not is constant. It's just a constant. Anyone got the answer? Is it the same? Is it the same? Is it the same? It's the same. Yes, the same. No, it's not the same. Yes. You mean the output process is gonna Ry is gonna be the same. Yes.
The same as the same as n naught.
Yes. So it's n naught over 2 times the delta of t or delta of tau. Okay.
So it's just like a time delay.
Yeah, but the time delay is not going to change. So think it over. Why it became out the same? This system is simply a time delay, right? So time delaying a random process is not going to change its autocorrelation function, right? Because autocorrelation function is dependent only on the time shift between the start and the second, right? But if you delay the whole thing, you will get exactly the same autocorrelation function. صح? But that's in terms of thinking. Calculations is easy to do. Anyone was not able to finish the calculations? You can work together, by the way. This is not an exam. Class activities you can discuss together. So you can finish it faster.
Practical application of this is just like to study a channel of a specific band of frequency, how the noise affects it.
Yes, exactly. Basically, to be able to incorporate noise with your analysis of the channel. So basically, across the channel, you have two random processes, right? The transmitted signal from your perspective as a receiver is a random process. And the noise from your perspective as a receiver is a random process. Both of them goes through a channel. So if you want to calculate the effect or the output of that channel given that input, you need to apply these. Okay. ها يا شباب. Anyone was able to get the output? Should be simple. Finished? No? Eh? هنا ما فيش statistics قوي، لكن الستاتستكس هتجيلنا في حاجات تانية. مالها الصيدات الأمريكية؟ But the examples or the problems that you will solve on this is quite simple. So basically the summary, the 3 pages summary that I listed, in addition to the some examples that we will solve, are going to be more than enough for you to understand what we are doing. You don't need to go into the deep math of this. Yeah, it's a new thing. Yeah. But by the way, this was supposed to be studied in your communication course. But anyways, okay? Did not happen, but it was supposed to. Anyways, so let me solve this example with you. So we have this delta of t minus 3, right? And we have this x of t, and we have this output y of t, and our rx of tau was equal to n naught over 2 delta of tau, right? Then, as we mentioned, the solution says that sy of f is equal to sx of f times square the magnitude of h of f, right? So, what's h of f? Number 1. Fourier transform of delta of t minus 3. What's the Fourier transform of delta of t minus 3? So, it's basically e to the minus 2 pi f 3 اللي هي t naught صح؟ 3. Okay? And then if you want to get the magnitude squared,
this is 1 squared.
Yeah, it's basically equal to 1. تمام? So that's one thing. We know this one. What's sx of f? It's equal to the Fourier transform, right? The Fourier transform of n naught divided by 2 delta of tau, right? Which is the Fourier transform of rx of tau, right? Okay? And this Fourier transform is equal to what? N naught over 2, right? Because the Fourier of a delta is equal to 1, right? In frequency domain. So that's our sx. Then sy of f is equal to the 1 times n naught over 2, which is equal to n naught over 2. Now what's gonna be ry, which is the required? It's the inverse Fourier transform of sy of f, right? What's the inverse Fourier transform of this? It's n naught over 2 multiplied by a delta of t, right? So simply, we went back to, right, same thing. It's the same. Why it's the same? As I mentioned to you. You have a random process. You put that random process through a time shift, which is your h of f, right? It's just a time shift. So what happens when you are calculating the autocorrelation of that random process? Does not change. Because shifting the autocorrelation does not cause any, starting the autocorrelation at any point is the same, as long as you take the same tau, right? So it's gonna be at the output, you are gonna have the same autocorrelation function as the one that you had at the input. The system is not gonna change the autocorrelation function. خلاص? Clear? That's how you can explain it physically. But في الآخر mathematically you can just get it and that's it. If I ask you a further question, why, explain, then you can say this. Yes.
But anyway, this is an LTI system, right? So in many cases, like time delays and only scaling up and down power spectrum, this will just be a scale of the input. Right?
Yeah, but then yes, but then it might not be only. So
It might be a square.
it might be. You're right, because this is linear and time invariant system. Then typically the output is gonna be shifted and scaled versions of the input. Well, yes, but at least here we did not have a scale. Tamam? So maybe in another system you will have something scaling, right?
We can only do this if it is stationary, right?
Of course. If it's not stationary, you cannot do the whole thing. We cannot even put this relation. Right? Because this relation is true only for the case of stationary, right? Because the only thing that has a power spectral density is wide sense stationary random process. Okay?
Another example?
We will do some other examples. Just wait. Okay. Now let's go to noise. Okay, because we are doing all of this to represent eventually our transmitted signal from the perspective of the receiver as a random process, as well as noise from the perspective of the receiver as a random process. Okay? Transmitted signal we will leave it a little bit because it has to do with pulse shaping. So after studying pulse shaping, we will understand how to represent our transmitted signal as a random process. Okay? So we did not do pulse shaping yet, so we will not go there. But noise. You know that noise, as I mentioned to you last time, it's actually included in your communication system as the receiver, because it happens because of the receiver's thermal noise in the electronics of the receiver, right? So this is the source of noise in our communication system. Okay? The thing that we call noise, there is other effects called interference. Interference is different. Okay? Interference comes from other sources. Okay? But noise is only when we say in communication system. Noise, we are talking about the thermal noise in the electronics of the receiver. Okay? And these thermal noises, you remember from your electronics, I think electronics 1, right? They can be represented as K, the value of the noise. Okay? Can be represented, the power of the noise can be represented as K times the temperature. K is Boltzmann constant, right? Times the temperature represented in Kelvin, right? Okay? Times G. And what was G? Yeah? Thermal noise, يا جماعة. Conductance of it's resistance. So you did not study noise خالص في electronics?
We
covered just the
theory.
Yeah,
As a theory.
ماشي.
we didn't find any equations regarding the noise.
Anyways, forget about this part. I was just focusing on, if you want to calculate the average power coming from noise, it's equal to, leave this, okay? It's equal to K times theta times G, where K is Boltzmann constant. Theta is actually the temperature, sometimes they're represented by capital T, but because we use capital T here for the period, so the text chose to use theta for the temperature, okay? But it's the temperature in Kelvin, right? And then multiplied by the conductivity of your piece of whatever, semiconductor or conductor or whatever, okay? So these three gives you the average value of the noise power. This is power, okay? Now, if we are thinking of noise, which is the case, as a random process, right? Then that random process can be represented by autocorrelation function in time domain or power spectral density in frequency domain. So the autocorrelation function is going to be the average power multiplied by an exponential, right, of tau, okay, divided by T naught, where T naught is equal to very physics quantity, which is the statistical average of time intervals between collisions of electrons inside the that conductor or resistor or semiconductor or whatever, okay? Typically, you just can take it as 10 to the minus 12 and that's it. تمام? So simply T naught is a constant equal to 10 to the minus 12. Okay? Now if you plot this, how it would look like? If you try to plot it as a function of tau. What do you expect? It's going to be something like this, مش كده? And it's with modulus tau, so it will be dropping on both sides, whether you are taking positive tau or negative tau, right? Okay, whether you are taking positive shift or negative shift, as you go away from the center, it will be dropping very quickly. تمام? Okay. Now, if you want to represent this in frequency, it's simply taking the Fourier transform of this. تمام? Now, taking the exact Fourier transform of this is going to end up with this expression: 2k theta g, so the same thing, right? Divided by 1 plus 2 pi f t naught squared. Okay? Now, t naught being a very small value, you can expect that for most of the frequencies, this term is going to be almost 0. So you can think of noise in the frequency domain as if it is almost a constant. And this is true because, again, forget about the division by t naught here, right? This expression, right, is going to be decaying, and the decay is going to be inversely proportional to this. So when this is a very small number, the decay is going to be very quick, right? So this is going to be almost as if it is, in time domain, a delta function. And the delta function in time domain looks like constant in frequency, right? This is why we call noise white noise, because in frequency domain, it has power at approximately all frequencies. Now, practically, it's not really all frequencies. It has values that are almost non-dropping up to 15 what? 15 gigahertz, right? And then after that, you start seeing a noticeable drop in the noise, okay? Now, since all or most of our communication systems are going to be here, it's quite safe for us to assume that noise is almost a constant in frequency, and in time, it's almost a delta function, the autocorrelation of noise, okay? Clear, why do we represent noise, and why do we represent it by? Number one, a random process, because it's random, right? And it is a function of time, right? Number two, why the power spectral density of noise is almost constant? Because of the fact that it comes from that autocorrelation function, and if you take the Fourier transform of that, it's going to look like almost a constant, okay? This is why we call it white noise. Remains one property that we need to describe. So now we have described the power spectral density, the autocorrelation, and we know what else? The time variation of noise, right? There is one property that we need to describe. What is it? It's random. So what do we need to describe for a random variable? It's the probability density function. So noise as a value is Gaussian distributed. The PDF of noise takes a Gaussian distribution. Why? اشمعنى Gaussian?
So that's around an average, goes up and down.
Don't try to explain it that way. Go back to your probability and statistics course. The Gaussian distribution is the normal distribution. صح؟ النورمال distribution ده كانت ايه البروبرتي بتاعته؟ ليه سميناه normal distribution؟
Concentrated around the mean. Concentrated around the mean.
Not necessarily, it depends on the variance. صح؟
Yeah, but it's
Depends. If the variance is large, it's not going to be concentrated around the mean. If the variance is small, the highest probability. Yes. But this is not the important property. Why do we call it normal distribution? Why it's called normal distribution?
This is why I called Gaussian for example.
No.
Continuous?
It's not the same. It's continuous, but why do we call it normal distribution? Okay. You remember the theory of large number, or what, the central limit theorem? صح? You studied central limit theorem. What does central limit theorem say? أنا هروح أنا هقفل وأروح. What does central limit theorem say? مش عايز exact statement. I want the meaning of central limit theorem. It says that if you add too many random variables together, regardless of the distribution of each one of them, you will end up with a normal distribution. صح? That's what central limit theorem is all about. If you have too many random variables, let's say one of them is uniform, the other one is binomial, the third one is whatever, the fourth one is Poisson, and so on, right? And then you get those random variables together, and you add them, so whatever value for the first that you get, and the second and the third, you add those values together, you will end up with another random variable, right? That random variable is going to be with normal distribution, regardless of the individual distributions of each one. Why is this normal? Why do we call it normal in this case? Because typically randomness in nature comes from too many sources, right? So for example, the temperature in this room is random. Whenever you measure it right now, and then you measure it a minute later, you will get some variation, right? What are the sources of this variation? You are breathing. He is breathing. I am breathing. I'm talking. Light is fluctuating. People are moving outside the room and causing some vibrations. Air conditioning is like going up and down. All these sources together, added together, cause the randomness of the temperature. So regardless of whether this is varying with uniform, I am breathing with Poisson distribution, you are talking with whatever distribution, right? The added of all of these together will end up with the temperature in this room being random with a normal distribution.
You mean
Because it's the sum now.
distortion, like distortion between the temperature?
If you measure the temperature in this room right now, and then you measure it a minute later in the same place, do you expect it's going to be the same or with some fluctuation? This fluctuation means that this temperature is random. Now where does this fluctuation happen? Why does it happen? It comes from all the different random sources. Tamam? These are added together. So if they are added together, regardless of the individual source of each of these, the end result is that temperature is going to be varying with normal distribution. So they call it normal distribution because in typical physical processes, right, the end result is that you will have some normal distribution of that process. Okay? Why? Because randomness in nature comes from too many sources. طبعا again يعني, so that we don't go into beliefs. Randomness here is from our perspective. Because as humans, we cannot get all these variables together and expect all their values and interpret all those values. So, but for Allah subhanahu wa ta'ala, no, it's not random. For us, it's random. خلاص? So that some people take this into belief. It has nothing to do with belief. خلاص? What was your question?
You said random distribution. Normal distribution. What's the other type? There's normal and there's...
There are many other types.
We need to compare between this and the other one.
There are many other types. There is a uniform distribution, for example. صح? There is something called uniform distribution. صح? This is not a normal distribution because it does not happen in nature. It comes from specific situations. Okay? But it's not the typical thing that you find. They call it normal because it happens a lot, not because it's normal and the others are odd. خلاص? The normality here comes from the fact that it occurs a lot. خلاص? Why it occurs a lot? Because typically randomness comes from many sources, and the central limit theorem says if you have many sources added together, the resulting distribution is going to look like the normal distribution, اللي هو البيل shaped, اللي هو الجاوسيان. Okay?
It's not a fact.
لا, the central limit theorem has a proof. It's not a fact. It's a theorem, so it has a
It's
proof.
called normal.
تاني؟
The word normal itself.
يا نهار ابيض يا جماعه. طب بص راجع الفيديو. خلاص؟ اوكي. I apologize that I mentioned anything about normal. خلاص؟ اوعى تقول لي why it's called normal again يعني. Yes. ها؟ Do you have a question؟ لا طيب خلاص. Okay. So for thermal noise, the end result of all these representations, and the one thing that we care about is that in frequency domain, it's represented by, and that's why I gave you the example of n naught over 2, تمام? Represented by constant value, n naught over 2, and in time domain, it's n naught over 2 multiplied by delta, right? Where this n naught is equal to 4k theta g. So 4 times the Kelvin, or Boltzmann constant, times the temperature in Kelvin, times the conductivity of your material, right? Okay? So what we care about really is that noise in frequency domain is n naught over 2 with constant value, and in time domain it's n naught over 2 at a delta, right? And does not exist anywhere else. That's the autocorrelation and the power spectral density of noise, okay? Now a question here, okay? If you have a power spectral density and you want to calculate the total power, how do you calculate that? So I have, for example, a power spectral density that looks like this, مثلا. This is my PSD, exactly, and this is frequency. So if I want to get the total power, what do I have to do? Yeah, because typically this is watts per hertz, right? And then in order to get the total number of watts, I have to integrate. So integrating over the curve will give you the total power. Now, if noise looks like this, right, and it exists in all frequencies, When you integrate this, what do you get? Infinity, okay? So the total power contained in noise is equal to? Infinity, okay. So how come any of our receivers work?
Because our receiver works with specific value.
Exactly.
So we are banding.
Yeah. So basically, at the input of every single communication system, you have to have something called a band pass filter, right? Band pass filter, which is working around your carrier. So this is your FC, and with the bandwidth of your the signal that you are interested in, right? So some W, right? And around the center frequency. So basically, out of all this noise that you have here, out of all this noise spectrum, you will only be getting this part and this part, right? The positive and the negative side, right? So your power is going to be only the ones contained here. So you'll have a limited power, right? Otherwise, none of our receivers will work. That's why at the input of the receiver, you have to have a band pass filter so that you limit the amount of noise that you are collecting from your electronics, okay?
So Doctor, do
Yes.
you mean that if we are using, theoretically, if we are using a receiver that receives
All frequencies
all bandpass,
will not be able to, yeah, it will burn maybe, yeah, all it will saturate لأن هو it will not burn لأنه في الآخر الباور طالعة من source عندك and the power جاية من ال air is really small. But the problem is your amplifiers will be overwhelmed by power of noise as compared to the power of the signal that you are interested in. So they will saturate at noise value and that's it. تمام? Because they will have more power of noise as compared to the signal.
Question
Yes.
about the definition of noise itself. You mentioned like generally noise, it's what is thermal noise.
Yes.
By noise we mean thermal noise.
Yes.
What we understood from previously, like noise, it's all natural sources of noise are called noise. But what man-made noise is called interference. So for example,
understood from what? From what I said or from something said?
no, from something like
Okay.
previous courses or
Yes, what did you understand? That everything that you're not interested in is called noise, right?
everything that's natural, not man-made,
Okay.
is noise.
Okay.
That's man-made is interference. For example, here we have background radiations. It's not thermal noise, so it's noise. But the definition that noise means thermal noise.
But
background
all
radiation
these, but all these, from the perspective of a communication system,
is extras are like what we don't need.
no. It's not only we don't need. They are very, very, very low as compared to the thermal noise in the receiver. So we only concern when we say noise in communication system, we only care about either man-made, which is the interference, or the noise that comes due to the electronics. The things that comes due to radiation and all these things, first of all, they are in bands that are different from the bands that we are receiving from. So they are already filtered out, right? And second, even the remaining parts are very low compared to the thermal noise, so you can simply ignore them because thermal noise is going to be your dominant factor.
Isn't thermal noise?
مش مديني فرصة أعطيك examples. Yes, go ahead.
Isn't thermal noise? It's like in the transmitter and the receiver, but we model it only in the receiver.
No, only in the receiver. Because we are modeling the noise added to the transmitted signal, not a signal inside the electronics of the transmitter, right? So we always care about the signal coming out of the antenna, which is already after everything in the transmitter, and then we have a signal, and then after that, it goes through the channel, then we collect it at the receiver, so the noise is added at the receiver. Okay?
Do you advise us to read the book? The book of the...
Read parts of the book. I mean, okay, the slides are extracted from parts of the book. So read the parts that correspond to what I described in the slides. The book, for example, goes in some, because the book is designed both for undergrad and postgrad. So for example, if you go to this part, you will find some theorems and proofs. I mean, don't really read those, okay? You'll find something talking about cyclostationary random process. That's a bit advanced, so I'm not going to describe it at this level, okay? It's something that if you do graduate studies, ممكن دقيقة واحدة أوقف الريكوردينج الأول، كويس؟ Let's try to do this example. Suppose that a white sense stationary white noise process. So this is your additive white Gaussian noise. So you are building this circuit, and then the input to this circuit is noise, okay? And that noise has a zero mean. Okay. Before going into that, sorry, so that things would make sense, I would prefer that we discuss the two properties of noise. So we have been last time we have been discussing how you look at noise as a random process, and then how you can get its power spectral density, right? So at time domain, you have the autocorrelation for noise, which ideally, right, would look like this, right? So something like a delta function, right? Approximately a delta function, and we assume it is a delta function, right? And this peak, of course, happens at tau equals 0, right? So at time domain, it's a delta of tau multiplied by some value, and that value we call it directly n naught over 2, okay? And in frequency domain, noise looks like constant value across all frequencies, and this is why we call it white, and its power spectral density, so this is Rn of tau for noise, and this is the power spectral density of noise, and it's equal to n naught over 2, right? This height for all frequencies, right? And then we discussed a little bit, because noise spans all frequencies, then at the input of any communication system, you have to limit the bandwidth by using a bandpass filter, so that you limit the amount of noise coming into the system. Tamam? Now that's from the analysis of that random process from the point of view of finding the power spectral density, right? But still, noise is random, and what describes a random variable or a random process in this case is the distribution of the random values, right? So these random values must have some probabilities, okay? Typically, noise is modeled as a Gaussian, right, random process, which means that the value of the noise, if you say, for example, that the variable n represents the noise, right, and this n must be also a function of t. That's why we call it a random process, right? But n itself is a random value. Remember, we described random process at the start of this chapter. It has randomness in its value, and it is a function of time at the same time, right? So the value of the noise at any point in time is a random variable, right? And that random variable follows the Gaussian distribution. You know what's the Gaussian distribution? It's the normal distribution, right? Okay? They call it Gaussian or normal. Does anyone remember the equation? You don't have to memorize it, of course. But does anyone, or bring it up so that I can write it here for your reference? So, Google it, that's fine. So that Gaussian distribution or normal distribution, it has two parameters. The first parameter is the mean, right? For noise, the mean is equal to 0. The second parameter is the variance typically, and for noise, it's a general variance called sigma square, and we call it sigma n, right? For noise, just to say that this is the variance for the noise, okay? Okay, what, error function? No, I don't want error functions. I want the, yeah, so 1 over, ما حد يملي يا جماعة.
1 over sigma.
Root of
2 pi sigma squared.
2 pi sigma squared, okay, multiplied by exponential. You call it e power or exponential, that's fine. Negative.
Open brackets, x minus mu.
X minus mu, which is the mean value. Okay. Squared.
Over 2 sigma squared.
Over 2 sigma squared, right? So this is the expression for your Gaussian distribution, and the sigma here is sigma n, and our mu is equal to 0, right, for the noise. So the noise has 0 mean, so the mu is equal to 0, and the variance is called sigma n, okay? So this is also sigma n. Okay. So what I wanted to say is our noise in general in a communication system is modeled as Gaussian random variable typically with 0 mean, so it doesn't have any mean, the mean is equal to 0, and with a particular variance, sigma n. And sigma n squared for noise is equal to n naught over 2. Nice, huh? So it's equal to the power spectral density. Okay? So the variance of the noise random process, the variance is equal to n naught over 2. Okay?
That's a property of noise, or
That's a property of noise.
just in this case, or
And no. That's generally the property of noise. That if you are given the variance of the noise, you can immediately know the power spectral density. And if you are given the power spectral density, you can immediately know the variance. خلاص. So this value is actually equal to the variance of the noise. The power هنا here we are talking about the autocorrelation power spectral density property of the random process. تمام. Here we are talking about the randomness of that random process. And the relation is that the variance of the randomness is equal to the power spectral density value. The constant power spectral density value. خلاص؟ كده يا شباب؟ عشان ما يجيش at any point in time when you are trying to solve a problem or design a system and you are told that the noise variance is this value and then you come and tell me, oh, I don't know what's the power spectral density of the noise. You already know it. Or vice versa. You are told you have a noise which is additive white Gaussian and it has a power spectral density of a value n0 over 2 given to you, for example, in milliwatts per hertz or whatever. Okay? And then you come and ask me, so what's the variance of this noise so I can model it? You already know it. Okay? Power spectral density value is equal to the variance of the noise. خلاص? So anyways, this noise is applied now to the input of this system. Typically, circuits are linear time invariant systems or not? Yes, no, why? Okay. The linear circuit, passive circuits. If you have passive circuits, which does not have any amplifiers or anything, okay? Are they typically linear or not? Number one. Yes, they are, right? Because if you, what's linearity?
If you added two inputs,
yes,
you will have the summation of the two outputs.
Exactly, and if you scale the input, the output is scaled with exactly the same value. That's linearity. The other part is time invariance. If you shift the input with a certain time shift, the output shifts exactly the same time shift. So typically, passive circuits are linear time invariant systems, and actually even circuits with amplifiers, as long as the amplifier is working in the linear region. If the amplifier is saturating, that's a different story. خلاص? So this is a linear time invariant system. Can you get the impulse response of this system? Yes. No? Try to solve. Get me the impulse response of this system. So the input here is going to be voltage, تمام? And the output is also the voltage across the resistor. تمام? Let's make it simpler, okay? Because you need to do integrals and differentiations and stuff, so it's easier this way. Don't get the impulse response, get the frequency response of this system. So give me capital H of F, okay?
R over J omega F plus R.
Exactly. So that's the straightforward one, right? So H of omega for this system is equal to R over
J omega L plus R.
R plus J omega L, right? Where omega is your frequency, so it's 2 pi f, right? So this is the input-output transfer function of this system. So that's the frequency domain. Now, if you want to get the impulse response, just do the inverse Fourier transform of this one, okay? and it's going to be not so nice, but it can be done from the tables. You don't need really to solve something complicated, okay? Anyways, if you have the frequency response, right, and you know the power spectral density of the input, the first requirement here is to find the power spectral density and the autocorrelation function of the output, right? So now for the input, we know the power spectral density is given by n naught over 2 constant, right? So take that, the power spectral density at the input, which is this, right? Multiplied by the transfer function, you will get the power spectral density of the output. Then if you want the autocorrelation, what do you have to do? Inverse Fourier transform of the power spectral density, صح؟ ايه يا شباب؟ نمتوا مني ولا ايه؟ ده احنا لسه بنبتدي. Simple. We know that this is a linear time invariant system. So the relation says y of omega, the output, is equal to x of omega multiplied by h of omega. But here we are dealing with power spectral densities, not magnitudes. We are not dealing with the amplitudes. So we have to put the other relation. What's the other relation for power spectral densities? S of y is equal to S of x, which is the power spectral density of the input, multiplied by magnitude of h omega square, right? So please calculate this from this, right? And then give me the expression of Sy. What's Sx? Yeah, it's constant equal to n naught over 2, right? So Sx is a constant value n naught over 2. Multiply that by that magnitude square, you will get the output power spectral density. حد يطلع لي expression for the output power spectral density? يا جماعة حاولوا تحلوا. The reason for doing the exercises is that you get practicing what we describe. If you just depend on what I describe and that's it, you will not learn the concept. خلاص? It should be simple يعني, but just you need to practice. Any expressions in the horizon? So y of omega is equal to?
I think it's n naught over 2 r squared over r squared plus omega squared x squared.
So n naught over 2 multiplied by r squared divided by
R squared plus omega squared x squared.
give magnitude, you are getting the magnitude. So بتعمل ايه؟ بتضرب this times its conjugate. Okay? So
r squared over omega squared L squared plus r squared. It's the magnitude only.
r squared divided by
Omega squared L squared plus r squared.
yeah, so r squared plus
And we need to also this all of this or two.
Which is the square root.
this is the magnitude only
Yeah, not square.
without square root. لا ما cannot be.
R squared.
This is already squared. مش كده؟ This is already magnitude squared.
No, it's only
R
magnitude.
squared plus 2 omega Lj.
r squared plus 2 omega lj. What's this?
No.
It's omega squared, 1 minus omega squared L squared over omega squared L squared plus 1 multiplied by R.
r squared
And
r طلعتها بره. and you don't need the root لان انت you're getting the square of the magnitude already.
Start this. Yes. Sorry.
r squared times هنا بتقول 1 minus omega squared L squared divided by omega squared L squared plus 1. That's okay.
ايوه بس انت مش عندك دي بس.
انت ايش
انت عندك
انا اسوي اصلا مقطع دي نمبر جيب
What is your answer?
My answer is wrong.
What is it?
No, I was trying simple system.
Anyone got the answer and sure of the answer? So R بس squared بقى. You don't need to take the root. So R squared multiplied by 1 minus omega squared L squared divided by 1 plus omega squared L squared. أعتقد ما. How did you calculate it?
I calculated the numerator as a number itself, so it's R squared. The magnitude of the numerator is R squared.
Okay.
And because R will be the same magnitude, and squaring this will be R squared.
لا بس this is not squaring this is squaring the number نفسه.
No, I take the magnitude of this one as well. The magnitude
of R divided by the magnitude. Yes. So divided over the magnitude of the lower one.
Yeah,
yes.
that's it.
So the magnitude of the lower one is
R squared plus omega squared L squared under the square root.
yes.
And squaring this one could give me this one.
Yeah. And is this different from what you got? They should be the same. انت بس كل اللي عملته انك خدت R square as a common factor outside, right? But then I think the wrong thing in yours is that it should be omega square L square divided by R square. When you take R square as a common factor. When you take R square as a common factor here, it should be omega L over R. So it becomes omega square L square over R plus 1. Otherwise, where did the R go?
Here, where did you take R squared?
هو في R تحت. كده ال R موجودة فوق بس وتحت لا. ليه مفيش R تحت؟ This is incorrect. بص على الدايمنشنز بتاعتها.
R should be here.
كده you have 2 impedances و 1 impedance تحت ما تمشيش. The omega L على R.
Take R from here. Take R from
Anyways, خلاص. So the expression is going to be as we see it here. Okay? So that's the correct expression. N naught over 2 R squared divided by R squared plus omega squared L squared. Yes.
يعني اطلع لي هالكلام R square plus omega square L square هذا ال H of omega بس. Because we have complex expression down. So we need to multiply by the conjugate.
ما انت when you multiply by the conjugate you get square the magnitude already. X time X conjugate gives you square the magnitude not the magnitude بس. So without any further squaring خلاص. هو ده كده خلاص. Okay. شباب. Okay. So if this is your y of omega, what's gonna be? So this is your sy, right? Of omega. So what should be the ry of tau? Anyone do the inverse Fourier transform for this? For this? Do the inverse Fourier transform for this. So this is a function of omega squared, right? تيبل حد يطلع التيبل من على الانترنت. So this resembles which one? Which is the one that has something in the denominator 1 plus omega square in the denominator? It has 1 plus omega square. Right? Because if you divide it over r زي ما انت عملت هيطلع لك في الاخر 1 plus omega square. 1 plus something square. Omega square scaled by a factor. Which one is this? It's cosine ولا sine ولا حاجة؟
I think it's cosine.
Exponential. Exponential? Okay. Exponential?
No, it's sine.
E to the j omega يعني?
Sine omega L over R.
E to the omega ولا ايه؟
It's sine of omega L over R.
Which one? 18? Okay, so that's the one that looks very similar. So e to the minus a magnitude t, right? So ry of tau is equal to نحاول بقى نطلعها من هنا هتطلع ايه؟ Given your expression. This is what we have. So compare this to yours and let's find out.
A is equal to R squared divided by L squared.
A is equal to
Wait a minute.
طيب النوت على 2 خليها بره. Doesn't matter and دي scaling factor بره خالص. تمام؟ And then we end up with 1 على 1 plus omega square multiplied by L squared over R squared.
بس ال A اللي فوق ما عملش سكوير.
انهي ايه اللي فوق؟ So you can say that this is n r, right? Take one r outside, and then you end up with r divided by r square plus omega square L square. بس ده ما ينفعش. أنت عايز الأوميجا تبقى without coefficient. So you have to divide everything by L square. تمام? So it will become r over L. And this one will be another r over L divided by r squared over L squared plus omega squared. صح? And then this is the frequency domain 1. So the time domain 1, so the r y of tau is going to be n naught r over 2L multiplied by e to the power minus the a in this case is r over L, صح? So e to the minus r over L multiplied by magnitude tau, right? And this, again, this is what you expect if your input is
real non-causal signal.
Yes, input is noise, which the r of tau is equal to delta function, right? And then that delta function produced what at the output? Decaying, something decaying with time. Isn't that what an RL circuit is doing? Yes. صح? So this is basically the output is something proportional to the impulse response of the circuit, right? And this is the expression, how the impulse response of the system looks like. تمام؟ لأن this system, if you put a delta at the input, it will give you something that decays with time. It will not just immediately go up and down in zero time. صح? And the same for RC circuit, right? Okay. So that's the output autocorrelation process, right? Sorry, the autocorrelation of the output process. Question: if the input is random process, the output must be random process because this is linear and time invariant system, does not have anything that will remove the randomness, right? Okay. The second part of the question was asking you, knowing that the input to the system had a mean value or an average value equal to, a mean equal to 0 and a variance equal to, what's the variance of the input? Random process. N naught over 2, right? What's the mean and the variance of the output?
0 and n naught over 2 scale.
Why? Why it's going to be 0 at the output?
Because the mean is the same, but the output will be a scale of the input.
The mean is the same. That's my question.
Because the input is a scale, up and down. So the mean of the scale values is just the same.
The system is just a scale. It's not
just scale. Not adding any new values.
The system is just scale. No, it did not scale. You got something totally different. And the input was delta. You got at the output e to the minus t. So it's not simply scaling, صح? The system is not simply scaling. You did not get a delta at the output. تمام? My question is, your answer is correct. By why? But why?
Because the mean is related to the time. So, in other words, you're actually affecting the function at this specific time instant.
You are affecting?
I mean, you're...
لا بص يعني rather than doing this, okay, yes, I think both of you are saying something descriptive, which is okay, but rather than doing it descriptively, do it actually mathematically if you want.
The system is positive, so it's like every input we are multiplying it by a positive value. So if it's a positive, it's going up. If it's a negative, it's going down. By the formula of the mean, if we are scaling up and down, we have the same number of samples. So in the end,
so you are getting much closer to the answer. So simply, if you want the answer, you know that this is a linear time invariant system, right? So the output must be, in time domain, must be the convolution of the input with the impulse response of the system, right? That's the output, right? Then if you want the expected value of the output, right, of y of t, this is the expected value of the random process, right, that they are looking for, the output random process. This is equal to the expected value of x of t convolution with h of t, correct? صح? The convolution is what? is an integral and time shifting, right? Then you will end up eventually with what? Assume that you do the time shifting with h of t, so that things are easier for you, tamam? Then you will end up with what? You will end up with eventually, this is gonna be h of t, right? Outside the expectation, right? And then the expected value of x of t, correct? صح? The expectation process is doing what? Is doing the expectation of whatever is random inside here, right? The convolution process is a linear process, right? It's integration and multiplication. So all the operations there are linear, right? And we know that also it involves some time shifting, right? To avoid confusion, even though time shifting is not going to change the mean, but even if you don't know that, assume that you are shifting this and fixing this, because in convolution you shift one, you fix the other, right? So assume that you are shifting the h, fixing the x, right? Then this expectation is going to be the expectation of something random multiplied by something deterministic. What happens in this case? The deterministic goes outside the expectation operation, right? So you end up with the expectation of x of t only, right? Convolved with h of t, correct? And the expectation of x of t is equal to 0. 0 convolved with something will give you 0. So the output expected value is going to be equal to 0 as well, right? What about the variance? The variance is more straightforward actually. Huh. Gaussian random process going through linear operations, right? Produces a Gaussian random process. صح? If you have something, random variable, which is Gaussian, and then you take it through any linear operation, you get a Gaussian. تمام? The new Gaussian will have a mean equal to maybe, but if you added something to that, it's not the old mean, right? So it's the old mean plus any deterministic additions, right? That one we already resolved. We know the mean. The variance is equal to
It will say the same variance.
Is it? The same variance. The system is doing scaling وحاجات زي كده صح? So, but you wouldn't be able to figure the scale. So how you look at it? The output is a random process, which is Gaussian, and it spans still all frequencies, right? Would not disappear from some frequencies, right? So you can easily look at this expression. Where is it? No, okay. Where is the expression I'm looking for? Okay, my argument is not totally correct because the output is not white Gaussian. It still spans all frequencies, but it is decaying with higher frequencies, right? It's R over R plus omega. So with omega increasing, your output random process is decaying. So you cannot assume that it is white. So the other option to get the variance is going to be what? The idea of scaling the system, right? Approximately what, sorry?
Approximately
No, this is not going to be approximately white, no. This with omega, this is going to be decaying nicely, yeah. And omega squared is down here, صح? So as you increase the frequency, the amplitude here will be decreasing, right? So this is not going to be white, it's not going to be constant. So in this case, the variance, you have to get it through the idea of Gaussian random process going through a linear system. Then the output, sigma, is going to be scaled by the factor of the system, right? So the factor of the system here is this magnitude. So actually the sigma is going to be a function of omega. The variance of this system is going to be a function of omega. I will check this because the variance should not be a function of omega. Now it looks to me like the variance is a function of omega. So I need to check this one, okay? So the mean is easy to get, but the variance, there's something missing. I will check the variance and come back to you, okay? Same concept, right? So the variance, the variance is defined as the expected value of y squared, صح؟ مظبوط؟ which is equal to the expected value of y of t times y of t. صح? But then this is equal to ry of tau equals ارفع
autocorrelation.
لا احنا ما نقدر نشوف راس
ما اكتب فوق يعني حاضر اهو المشكله بقى البتاع ده يقعد ايوه يقعد يجيب لي حاجات فوق حاجات تحت. Is it clearer now? Okay. So what's the autocorrelation? It's the expected value of y of t times y of t plus tau or minus tau. تمام? Okay. So if it's y of t times y of t, it must be that tau is equal to 0. So it's equal to at tau equals 0, but what's ry of tau? It's this. صح? So we already know ry of tau. So set tau equals 0 here, you will get, this will disappear and you will get only what? N naught r divided by 2L, and this should be your variance, right? From the definition. Variance for, but keep in mind, this is the variance only for the case that y is with 0 mean. What if y had a mean? What's the definition of the variance in that case?
y of t multiplied by
Minus al-mean squared, directly. You can put it in one of two ways. It's the expected value of y of t minus mu, and then you square all of this, right? This is the variance. Or this is the same as saying y of t squared minus mu squared, right? That's what we learned even in your probability course. You calculate the variance this way or that way, you get the same thing. In this case, mu was equal to 0. So variance is directly expected value of y squared of t. And this is the autocorrelation at tau equals 0. This is the autocorrelation. So put tau here equals 0, you will get the variance, which is n naught divided by 2L multiplied by r. Tamam? So your variance, sigma square of y, is equal to ry of tau equals 0, which is equal to n naught r over 2L. صح? This function when you put tau equals 0. خلاص؟ So